Okay, any question from 8.1, 8.2? Remember the hard question I did last time? Yeah, it turns out to be that ugly. I did it like many, many times. I get pretty much the similar answer. Any question? Let me know from chatting or from your chat message or from, just let me know. If not, I go ahead to 8.3. Okay, nobody say anything. I do 8.3. 8.3 consists of two big parts, and they are big parts. 8.3, application to physics. To physics and engineering. The first one is on hydrostatic pressure and force. The second is center of mass for lamina. Center of mass for lamina. And moments for lamina. They are not connected pretty much. Okay, so I can do part B first and then part A. But we will basically spend our day today doing this 8.3. And if I have a chance, I start chapter 10. I will skip chapter 9. I will also skip 8.4 and 8.5. Let me start with part B. Let me start with part B. Okay, a moment. And center of mass for lamina. So I do part B first. Let region R be bounded above by y equals to fx and below by x-axis. Then if R has uniform density rho, the moment, I think I should say the first moment. The first moment with respect to y-axis is given by moment with respect to y-axis equal to integral for a to b of x fx dx, where a and b are the zeros of fx. So suppose I have this here. I think I should say, yeah, so this is y equals to fx. Okay, this is region R. This is A and B. Okay, the moment with respect to the y-axis, you have A here. I mean, you have from A to B, you see the boundary of this region here, right? Okay, and then you insert x, and this is the function. Actually, I need to put the density row outside of that. I forgot that row. Now, so that's moment with respect to the y-axis. Now, moment with respect to the x-axis is 1/2 times rho from A to B of fx being squared dx. Now, don't ask me what is the moment for now. Okay, for now, don't ask me. It's just formula first. The moment with respect to x-axis, the moment with respect to y-axis, okay, are given by this. We will first learn to compute these moments, and then later on we will come back and I will come back and explain what it has to do with the center of mass. Okay. Now, let's say for example, suppose I have let fx equals to x squared plus 2. And actually, I don't need that from A to B. Where is the 0? I don't need that. I'm sorry. I don't need this. I don't need this. My bad. My bad. I need to erase this. For x between A and B. That's good enough. It doesn't have to be the zeros. Like for example, my x here, I will make it from 1 up to 3. Okay, so pictorially, it looks like the following. X squared plus 2, okay, from x equals to 1 up to x equals to 3. So our region is this region here. This is our region. Now, the density is constant rho. So the moment, part A, moment with respect to y-axis is rho times integral from 1 to 3 times of x times fx. That's the moment with respect to y-axis. Okay, what does moment, the first moment with respect to the y-axis, that's something I will explain to you later on. Okay, but this is the setup, and then from there you integrate. This is integral from 1 to 3. It's quite boring at this point though. X to the 4 plus x squared from 1 to 3. Then it's rho times 81 over 4 plus 9 minus 1 4 plus 1. So there will be 20 plus 8, that's 28 rho. Part B, what about the moment with respect to x-axis? That's 1/2 rho integral from 1 to 3 of x squared plus 2 squared dx. That's equals to 1/2 rho integral from 1 to 3 x to the 4 plus 4x squared plus 4 dx. 1/2 rho 1/5 x to the 5th plus 4/3 x cubed plus 4x from 1. It's 243 over 5 plus 27 times 4 is 108 over 3. 27 times 4. Plus 12 minus 1/5 plus 4/3 plus. That's 242 over 5 plus 104 over 3 plus 8. Yeah, I don't really want to compute it, honestly. But anyway, I do it. No choice. I factor 1 over 15. So 7 to 6 plus 5 times that is 520. 15 times 8, 3 times 4, 120. What is this? 640 plus 7.6. 1366. Ah, that's not a nice number, huh? I get 45.5333 or 5 decimal places. Or you can just leave it as fraction too, but please simplify that. Okay, I can reduce at least by 2. So there will be 683 over 15. I prefer this one. Now, center of mass center of mass is given by the coordinate x bar, y bar, where x bar equals to the moment with respect to y-axis over the mass, y bar is the moment with respect to x-axis over the mass. I somehow think, yeah, that's right. Now, the mass itself, you will see, is equal to rho times the area of R, which is basically rho times a to b of fx dx. Okay, so if I go back to that question, part C, for example, what is the mass? The mass is equal to rho times integral from 1 to 3 of fx, x squared plus 2. That's 9 plus 6 minus 1/3 plus 2. 15 minus 2, 13, so that's 12 and 2/3. 28 over 3 rho. Let me see. This is rho times 13 minus 1/3. That's 12, 2/3 rho. 26 and 17. Yeah, that's the mass. Therefore, part D, my x bar will be moment with respect to y over the mass. Where is moment with respect to y? 28 rho. Moment with respect to, and the mass will be 28 over 3 rho. That's equals to something not right here. No, something not right here. This is so not right. Give me a second. Good thing I computed. Do I make miscomputation somewhere here? Duh. I'm sorry. This is not right. This is not right. This is 38 over 3. That's 38 over 3. So it won't be 3. I know it won't be 3. So this would be 28 times 3 over 38. I can reduce by 2. 14 times 3 is 42 over 19. That's my x bar. My y bar will be the moment with respect to x-axis over mass. That's an ugly number as I remember it still. 683 over 15. 683 over 15 rho over 338 over 3 rho. The rho cancels. 683 over 15 times 3 over 38. That's 5. So this 683 over 190. I don't think I can reduce this. So from there, the center of mass is 42 over 19, 683 over 190. Okay, let's do a problem from our textbook. For example, number 26. Number 26. After this number 26, I will explain the idea behind this formula. So that's where we actually learn how to build an integration. And then, and it will be quite a long explanation. And then we go back and do some other problems on this center of mass. Number 26. Sketch the region bounded by the curve and visually estimate the location of centroid, which is the center of mass. Okay. Find the exact coordinate of the centroid. Maybe I explain first. The word centroid is equal to center of mass of lamina. Now, lamina itself means the region, two-dimensional region with constant density. Or uniform density. Okay, now this lamina is bounded by y equals to square root of x, y equals to 0, that's x-axis, and x equals to 4. So if I try to picture that, that's a curve like this, that's y equals to square root of x, bounded below by y equals to 0, and bounded on the right hand side by x equals to 4. So what is the center of mass of this region here? For those who already taken physics, you know center of mass actually refers to the coordinate of a body, in this case two-dimensional body, such that you can hold that, let me grab a paper, such that you can hold that body, in this case lamina, at that point and it is balanced. Let's say you look at me now. Let's say this is my lamina, just a piece of paper. Okay, let's say that's my lamina. Then the center of mass of this lamina is the point that I can put one point on that two-dimensional plane. There are zillions of such coordinates. Okay, now I pick one of that point, okay, such that the whole structure, the whole lamina, the whole region is balanced and not tumbling. That's what we call the center of mass. Okay, that's what we call a center of mass. In calculus 3, you will do center of mass of three-dimensional body. So I need you to know how to set up the integral for the two-dimensional body for now. Okay, and this one is a rectangle, right? You see this is a rectangle. It is easy to find the center of mass. The center of mass of a rectangle is actually, if I fold it in half and then I fold it in half this way. You can do this experiment yourself. Grab a paper, okay? And then the center of mass must be the intersection of those two points, okay? And believe it or not, if you use the same rectangle and you fold it diagonally, okay, the crease that you created by doing the folding will also intersect that point. It will also intersect that point. Okay, that's the center of mass of a rectangle. You will see that's an important information for later. Let's go back to our drawing board. And it will help us to develop the formula later on. But how do we compute this then? The center of mass or the centroid of this region. Well, first I will compute the mass. The mass equals to rho times integral from 0 to 4 times the y square root of x dx. That's rho times 2 over 3x to the power of 3 halves from 0 to 4. That's 8 minus 0, huh? So that will be 16 over 3 rho. How about the moment with respect to y-axis? Moment with respect to y-axis is rho times integral from 0 to 4. Okay, x times square root of x dx. You will see moment with respect to y. Moment with respect to y, basically you insert an x here. Basically that's what you do. Okay, and why we insert x, that's something I will explain to you later on. This is equal to rho times, that's, let me just write it in exponent. So this is x to the power of 3 half dx. So this is rho times 2 over 5 x to the power of 5 half from 0 to 4. That's rho times 2 32 minus 0. So that's 64 over 5 rho. Moment with respect to x-axis will be 1/2 rho integral from 0 to 4 square root of x being squared dx. That's 1/2 rho integral from 0 to 4 x dx. So that will be 1/4 rho times 16 minus 0. That's 4 rho. Now then, what is the x bar? X bar equals to the moment with respect to y-axis over the mass. 64 over 5 rho over 16 over 3 rho. The rho cancel. I get 64 over 5 times 3 over 16. That's 12 over 5. Well, the y bar will be the moment with respect to the x-axis over mass equals to what? 4 rho over 16 over 3 rho. That's 4 times 3 over 16. That's 3 over 4. So the centroid is at the center of mass is located at 12.5 12 over 5 comma 34. In decimal, that is 2.4 comma 0.75. So to visualize that, 2.4 approximately here, it's approximately like this here. So approximately this is the central mass. If you cut a paper with this shape, right? If you make it exactly to the scale, and you hold it the paper right at that point, 2.4, 0.75, then that cut of paper will be stable, will not tumble. In general, I don't like this generalization, but our textbook does it this way, so at least I mentioned it. So x bar, y bar is given by, you will see the rho because it's both of them constant, the rho will always cancel. Okay, that's not the case in calculus 3. In calculus 2, we still deal with lamina, therefore the rho, the density is constant everywhere, and therefore they will cancel. Okay, it becomes integral from a to b of x fx dx over integral from a to b fx dx. Notice that the rho cancels. Okay, and then here we have 1/2 integral from a to b of fx doing square dx over the rho cancels at the bottom, rho times the area. That gives you the mass of that lamina. The question is why? Why the formula looks like that? I will do this in 2 stages, maybe even 3 stages. First one, I want to explain the center of mass in 1 dimension. Okay, now suppose we have a line here. Let's call this our 0. And I put some masses. Let's say I put a mass here, mass 1 located at x1, and mass 2 located at x2. Suppose the weight or the mass of this bar here is negligible. So you put this mass on a bar, okay? Now the question is where should I put the fulcrum? Where should I put the fulcrum, which we will call x bar later on, such that this will be balanced? Okay, so imagine you have this situation, and again the bar is negligible. Now the thing is, it will be balanced if the left hand moment times the right hand moment are equal. What is a moment in this case? The first moment refers to the distance here times the mass. The distance here times the mass. So it will be balanced if the moment on the left hand side is equal to the moment on the right hand side. The mass times the distance from that X bar. Now the thing is, we don't know the location of that X bar. We don't know the location of that X bar supposed to be. Okay, now how do we solve this? How do we find that? From this picture, you see that D1 is equal to X bar minus X1. You see that X bar is to the right of X1, right? While D2 is X2 minus X bar. Okay, I will distribute. And I will collect X bar on the same side. So X bar times M1 plus M2 equals to M1 X1 plus M2 X2. So X bar equals to M1 X1 plus M2 X2 over M1 plus M2. Which if you think about this expression here is basically the mass multiplied by the distance from origin. And this expression here is the product of the mass times the distance from the origin, divided by the total mass. And this is the center of the X bar, the fulcrum, the position of the fulcrum, the center of mass of these two masses here. In other words, if you put your X bar right here using this formula, then this bar will be balanced. It will not tilt to the left, will not tilt to the right. By the way, do not underestimate this formula though. Do not underestimate this formula. Do not underestimate this formula. Back in beginning algebra, I wonder if you remember mixture problem. If you remember mixture problem can be done a lot faster using this physics technique. So when I taught beginning algebra, there's a mixture problem there. I taught my students, of course, the right way to do it. And then from there, like 1 week before the department final, I taught them how to do it using shortcut. And the shortcut actually coming from here. Okay, if you want to know, then you can set up an appointment with me on Saturday during my office hour on Saturday. Then I show you that little secret. It would be nice. This one is 1D. It's only one dimension. It's a line, right? It's a line. Okay, so if you put masses on one dimension, that's what the position. Now the thing is, let's generalize that. What if this is, you will see that this formula is basically the sum of MIXI over the sum of mi in sigma notation. Now, you can see that this can be the formula if we have more masses. Not only two, let's say you have 3 or 4 or 5, and so on and so forth. Okay, now to go even further, what if at any point of x there is a mass? Okay, and let's say the mass is a function of the region. So all of the sudden, maybe I put question mark here. Then our x bar is equal to, now this sigma notation here will become, the sigma notation there will become integral. Okay, the xi becomes x, the m will be rho times fx dx. Maybe I do it this way. The mass will be rho times fx. The xi this becomes x. While at the bottom, this sigma notation will still be integral, while the m will be rho fx. Okay, we can factor the rho out and cancel. Now, then what happens if then we extend this to 2 dimension? I extend this to 2 dimension. Okay, and I have a curve. Let's say my curve like this. This is from A, this is from B to B. And yeah, of course, at any point here, at any x, there is a mass. The mass is basically the density multiplied by the length of that line. Or if I make it like a very small rectangle here, this is way too small. Then this will be dx. This will be the height fx. Okay, that's the area of the rectangle multiplied by the density rho. So the mass here, the little mass here, okay, will be equals to the rho times fx times dx. Just for that one section, the mass is that. Now, how about the moment for that part? The moment for that part is moment with respect to the y-axis for this part. The moment with respect to the y-axis is basically that mass multiplied by the distance from the y-axis, which is x. So the moment with respect to y-axis just for that strip there is x times rho times fx times dx. Now this is the area of a rectangle. Multiplied by the density, give me the mass of that strip. Multiplied by the distance from origin, give me the moment. Okay. Now the thing is then, what is the moment of the whole region? What is the moment of the whole region? And basically you integrate all those masses of those strips and all the moments of those strips. Okay, so the total mass will be the integral of rho fx dx. Okay, and the total moment with respect to y. This is only for that one strip. This is only for that strip. Only for this strip. Now, then the total moments for all those strips in this region will be integral from a to b of x rho fx dx. Okay, that's actually how we build. And when we say moment with respect to y-axis, is basically the mass. It's basically the mass multiplied by the distance from the y-axis. That's why we call that moment with respect to the y-axis. Okay. Now then, how do we build the moment with respect to x-axis? How do we build the moment with respect to the x-axis? Now remember, if we have a rectangle, then the center of mass is right in the middle of that rectangle. Right? If I have that rectangle, the height is fx, the width is dx, the center of mass is right in the middle. This is 1/2 of fx. So the moment with respect to the x-axis, just for that one strip, will be the distance from the x-axis is 1/2 y, right? 1/2 y, let me use y for now, times the mass of that strip, rho times fx times dx. But y and fx are the same, right? That's just for that one strip. Now for the overall region, the moment with respect to the y-axis will be the integral of that thing. 1/2 rho is constant, so I can pull it out from a to b of fx being squared dx. Using the same idea, let's see, number 28, for example. I hope by you developing the formula, you can build that formula on your own later. Let's say number 28, we have the region is bounded by y equals to sine x, y equals to 0, and the x is between 0 to pi. So basically, I have this, the sine function from 0 to pi, okay, and this is y equals to sine x. By visualization, you can tell that the x bar should be pi over 2. Right? X bar equals to pi over 2. We will do it by computation later on. Now the thing is, where is the y bar? We still don't know that. I will still compute the x bar, okay? Even though visually we know that will be pi over 2. Let's compute it one by one. First one, if I were you, I'll compute it in this order. Find the mass first. The mass will be rho times integral from 0 to pi of the function. Okay, this is equal to 2 rho. Before I go too far, at calculus 2, I do expect you to know the following. The area from 0 to pi over 2 for sine x is equal to 1. That's why then you know that this we have symmetry here and there, right? So the area there must be 2. You can do your computation, go ahead. Right? But I will be yawning when I see you doing that. You can see this here. So integral from 0 to pi over 2 of sine x dx. That will be equals to negative cosine x from 0 to pi over 2. That will be negative of 0 minus 1. So if you go on one more period here, then it will be another one, right? So how about the moment with respect to x-axis? Moment with respect to x-axis. I'm sorry, with y-axis will be rho times integral from 0 to pi x sine x dx. Do integration by parts. That is equal to negative x cosine x plus sine x from 0 to pi, don't forget the rho times that will be negative pi times negative 1 plus 0, that's for pi, minus 0. Oh, okay. Yeah, 0 plus 0. So this is pi rho. You see that x bar, at this point we can compute x bar already. X bar equals to pi rho over 2 pi. Confirm, right? Our x bar is pi over 2. How about then the moment with respect to x-axis? That's 1/2 rho integral from 0 to pi sine squared x dx. That's 1/2 rho times 1/2 integral from 0 to pi 1 minus cosine x. I can tell this will lead me to 0. But y times, imagination, integral from 0 to pi of cosine 2x dx. I want to say this is equals to 0, but why? The period is pi. So it's cosine pi here. Right? Cosine 2x, the period is pi. Okay, but the area in the curve, this is 1, this is -1, this is -1, this is 1. When you add all of them, that's 0. I mean, come on, it's one period. Right? So the area above and below altogether should be 0. So then here I will get pi over 4, pi over 4 rho. So y bar equals to pi over 4 rho over 2 rho, that's pi over 8. So the centroid is pi over 2 as we expect, comma pi over 8, which we did not expect earlier. Okay, so if I look back to that graph here, this should be, yeah, this is the y bar equals to pi over 8. Okay, so if you hold, you have that shape, you hold it right at this coordinate, that shape, that lamina will be balanced. It will not tumble. It will not tilt in any direction. If you take my calculus 3, I can explain more about center of mass, okay, and explain further why we are grateful that your center of mass, the center of mass of your body should be your heart, should be your heart, right at your heart, at the bottom of your heart, as I know. Furthermore, let's see how about number 32. Find the centroid of the curve. So the region, sometimes I use R, sometimes I use D. Number 32 is bounded by y equals to x cubed, x plus y equals to 2, and y equals to 0. Y equals to x cubed, it's supposed to be like this, right? Y equals to x cubed, and then x plus y equals to 2. This is x plus y equals to 2, and then y equals to 0. So it refers to this region here. Find the center of mass. Find the center of mass. Find the mass first. Find the mass first. I think I happen to pick a hard question. I will skip this one. I will do this later. In a second. I do this later. I do this later. This one is a bit too hard right away. Too hard for you, not for me. Let's do number 30 first. Number 30, the boundaries, the region R is bounded by y equals to 2 minus x squared, and then y equals to x. Two minus x squared is something upside down problem. This is 2, this is square root of 2, and then y equals to x. Oh, what is the intersection here? What is the intersection there? Let's find out. That's when y equals to x is equals to 2 minus x. 2 minus x squared. So x squared plus x minus 2 equals 0. So x equals to -2, definitely not the 1 we want, x equals to 1. So this is 1 comma something. It must be 1 comma 1 then, huh? Must be 1 comma 1. This is the lamina. So then what is the mass? The mass will be rho times integral from 0 to 1.
Wait, how do we know it's not the other one, other region?
Well, because this is definitely in the first quadrant.
But isn't the other, the one below it, like from root 2 to 0, also in the first quadrant?
Hold on. You are right. Thank you. Good thing you mentioned it. I'm totally wrong with by canceling this. No, not supposed to. Because it doesn't say that it is bounded by the y-axis. It doesn't say that it is bounded by the y-axis. So it must be the one like this here. Should be this part. You see? Right? Okay. So this is actually -2 comma -2. So good thing is you stop me. Otherwise I will get the wrong computation. Is it better right now? The region here says that it is only bounded by these two curves, this guy and this guy. It doesn't say that it is bounded by x-axis or y-axis. So the only region that is bounded by these two curves is the yellow region. Okay? Then, so the mass will be rho times integral from -2 to 1 of, okay, what is the area of this one little box here? What is the area of that little box there? That's dx times fx minus gx. 2 minus x squared on the top minus x at the bottom. That is equals to rho times negative integral from -2 to 1 of, oops, sorry, I can just integrate it right away. This is rho times 2x minus 2 over 3x cubed minus 1/2 x squared from -2 to 1. That is rho times 2 minus 2/3 minus 1/2 minus, when x equals to -2, this is -4 plus 16 over 3 minus 2. What will that be? Where do the 2/3 come from? When x equals to 1, this is 2/3. Oh, you mean that? Okay, thank you. It should be 1/3, huh? Should be 1/3 here, so this will be 8/3. Okay, is it better now? Okay, so 2 minus -4 is 6. -1/3 minus 8/3. So minus 8. No, it becomes plus. And So that's negative 3 plus 1.5. What will this be? 7.5 minus 3, that's 4.5 rho. That's for the mass. Or another way to say it, the area of this, the yellow area here is simply 4.5. Simply 4.5. Unless I make miscomputation, I don't think so. Okay, how about the moment with respect to the y-axis? The moment with respect to the y-axis will be rho times integral negative 2 to 1 of x times the top function minus the bottom function. Okay, that's equals to rho times integral from negative 2 to 1 of 2x minus x cubed minus x squared. It's x squared minus 1/4 x to the 4th minus 1/3 x cubed from negative 2 to 1. So times that's 4 minus 4 plus 8x. What is this here? Cancels. Okay, so 1 minus 1/4 is 3/4. 3/4 minus 3. That's 12. So that's negative 9 over 4 rho. So x bar, at this point we can find the x bar already. That will be negative 9 over 4 rho over 9 over 2 rho. That's negative 2 over 4, negative 1/2. So if we look back into our graph here, the position for the x bar will be slightly to the left of the y-axis. This is our x bar. X bar equals to negative 1/2. Now, how about the y bar? To find the y bar, I need to first compute the moment with respect to x-axis. That's 1/2 rho integral from negative 2 to 1 of fx squared minus the lower one squared. You don't subtract and then square. You square each one of them first and then you subtract. This is 1/2 rho integral negative 2 to 1. 4 minus 4 minus 5 x squared plus x to the 4 dx. It's 1/2 rho 4x minus 5 over 3x cubed plus 1/5 x to the 5th from negative 2 to 1. When x equals to 1, that's basically the coefficients. when x equals to -2. Yeah, that's quite ugly. This is 1/2 rho. Let's see, the constant 4 plus 8 is 12. That's minus 45/3, that's 15. Plus 33/5. So that's 1/2 rho minus 3, 15, or 18, 18/5. Am I right? So that's 9/5 rho. Now y bar equals to 9/5 rho over, what's that? 9/2 rho, is that 9/2 rho. So this is 2/5. The centroid is therefore what is the x bar? Negative 0.5, comma 0.4. That's for the centroid. For this number 30, number 30. Number 33, I mean 32. Why do I say this is more difficult? Because in my opinion, if you use x as your point, as your variable of integration, it will be difficult. At least you need to deal with these two portions here. Let's say for the mass, right? For the mass will be rho times integral from 0 to, what is that? I need to find the intersection here, right? Let me find that first. X plus x cubed equals to 2. When x equals to 1, it will work, right? I'll just do it by guessing. Okay? X equals to 1 and therefore y equals to 1. Agree? When I try to solve this problem, right? Okay. So that will be integral from 0 to 1 of x cubed dx plus integral from 1 to 2 of 2 minus x dx. I think you can do this. This is not too hard. Right? This one is okay. Right? This one is okay. So this is rho times, this will be 1/4 plus 2x minus 1/2 x squared from 1 to 2 that's 4 minus 2 minus 2 minus 1/2. That's 3/4. I'm sorry. Yeah, 3/4. That's 3/4. How about the moment with respect to y-axis? That will be rho times integral from 0 to 1 of x times x cubed dx plus integral from 1 to 2 x times 2 minus x dx. So that's rho times integral 0 to 1 of x to the 4th dx plus integral from 1 to 2 of 2x minus x squared dx. That's rho times the first integral will give us 1/5. That's x squared minus 1/3 x cubed from 1 to 2. That will be 4 minus 8 over 3 minus 1 minus 1/3. That's 3 minus 7/3. Let me factor 1 over 15 out. Avoid using calculator too early, because once you use calculator here, there will be too much approximation. So this will be 3 plus 45 minus 35. And that's 13. So this is 13 over 15. Therefore, my x bar, we can find it right now, is 13 over 15 rho over, what is the mass? 3/4 rho. So that's 13 over 15 times 4 over 2. Oh, shoot, nothing to cancel. 42 over 45.
Thirteen times 4 is 52.
52, thank you. No wonder. Thank you. I didn't realize that though. But I knew something not right. Okay, because if you compare, notice that the region here is larger than the region here. Right? So for that to balance, then my x bar is supposed to be a bit to the right of 1, not to the left. You see? Okay. I mean, just visually seeing that, right? Notice that the region on the left-hand side is less than the triangle on the right-hand side. Okay, so it's heavier on the right-hand side. If my center of mass to the left of 1, it will definitely tilt to the right. Does it make sense for you? That's why I get slowed down earlier. But thank you. That's a correction I need though. Okay, that's for my x bar. How about my y bar? Okay, I need moment with respect to x-axis. That's 1/2 rho integral from 0 to 1 of x cubed squared dx plus integral from 1 to 2 of 2 minus x squared dx. I will finish this and then I'll give myself a break. This is integral from 0 to 1 of x to the 6 dx plus integral from 1 to 2 of 4 minus 4x squared plus x. I'm sorry, 4x plus x squared. This is 1/7 plus this is 8 minus 8 plus 8/3 when x equals to 2. When x equals to 1, it's 4 minus 2 plus 1. You don't have to compute it the way I do that. So that will be plus 7/3 minus 2. Oh, that's a negative number. Oh, no, it's not a negative number. No, it's not. Because this is 1/7 plus 1/2, right? So that will be 10/5 of 5/21 rho. Therefore, y bar equals to 5/21 rho over 3/4 rho. Hold on. I wonder what is this. I didn't put that here. But that's 3/4. So that would be 21/63. Nah, what 20? 20/63. Finally, so my x bar, y bar will be something, 20/63. 52/45. Okay, that's where I'm gonna stop for this 8 point. No, I don't stop this 8.3. I want to stop for my break. We come back at 8:55. Let me name this 8.3b so that we are aware this is the B part. And the A part is done after. They are not related actually. Nearly not related. I mean, for our level, they are not related. So 8.3 part A, that's hydrostatic pressure and force. Part B, moments and central mass. What we will do next is the hydrostatic pressure. And force. Unfortunately for this one, I really have to develop that. I will start with this first claim. The claim, the pressure at the point with depth d from the surface of fluid depends on the depth and density of the fluid. We call that rho. Okay, of course, depends on the gravity G also. Pictorial, suppose I have a container with water. Let's say the water at this level. Okay, then the pressure experienced by this point here, the pressure experienced at that point there is basically depends on how deep it is from the surface of the water and the density of the water. In this case is rho. Okay, in fact, the pressure P, we can say the P is equals to the depth D times rho times G. Okay. Why? Proof. Proof. Imagine this in 3 dimensions. From the water up to here. Let's say P is actually somewhere in the middle. Okay. Now, then let's take a look on how much pressure being experienced at the bottom of this. So instead of observing at that point that red dot there, we take a look at the bottom. Okay, and let's call this here the height of the water. Okay, now the pressure at the bottom, is equal to the mass of the water or the mass of the fluid divided by the area. Actually, not the mass though, it's actually the force. It should be the weight of the water, not the mass. the weight of the water, divided by the area at the bottom. Now the weight of the water is equals to rho g times the volume. To be more precise, the weight is equals to the mass times g times the gravity. But the mass is equals to the volume times density. That's the mass times g. Again, the area here is the area in the green. But the volume is the area times the height times rho times g over the area, and you see the area here cancels. So the pressure at any point at the bottom, is actually equals to the height to the surface of the water multiplied by rho times g. That's at the bottom. Now what happens if it's floating here? Well, basically, however deep it is from the surface of the water times rho times g. Okay. Now, of course, in this case, if I am interested, let's do some problem. Suppose I try to make an easy problem now. Suppose, for example, you have water in the length equals to, let's say, 10 meters. The width equals to 8 meters. And the height equals to 6 meters. That's a very big pool of water. Let's say that's your water. I don't like that. Maybe. So this is your whole water here. You fill it up full. This is 10. This is 8. And this is 6. And when we say hydrostatic, it refers to that the fluid, or the water in this case, is not moving. Okay, it's static. Okay, so part A, find the hydrostatic force at the bottom of the pool. So the force will be equal to, notice that any point at the bottom of this pool have the same pressure because they all have the same depth. The depth is all 6. Okay, so it will be the pressure times the area of the base. Now the pressure is the depth times rho times g times area of the base 10 times 8. That's 480 rho g. I would just leave it in rho g, okay, because I don't remember what is the density for water. I know that's actually 1 kilogram per cubic decimeter, or 1,000 kilogram per cubic meter. Huh? 4.18? What 4.18? What 4.18, by the way? Explain to me. I don't think so, though. I don't think so. The density for water, as I know, is 1 kilogram per liter. 1 kilogram per decimeter cube. Or if I make it into meter cube, it will be 1,000 kilogram. That's the density for pure water. In metric. 4.18, I think, is for something else. I don't know. But I would just leave it as rho, okay? And then if instead of dealing with water, if you deal with other fluid, then you can easily change your rho. You say you get 4704000. What's that? The force in Newton. Oh, wow. Okay. I don't even go that far. I would just leave it like that. Okay, well, as I know, then G will be 9.8 meter per second square. Is that right? So if you multiply that, let's see, this is 480 times 1,000 times 9.8. That would be in Newton. Let's see. Even that 9.8 is actually approximation there. Yeah, that's right. That's 47040 with extra 3 zeros. Yeah, but I usually don't. I will just leave it as 480 rho g. Okay, your textbook will go this far. This is your textbook. With me, you can just leave it like this. Okay, unless you want to compare your answer with the textbook, then that's what you do. Okay, now, by the way, this is in metric. This is the unit in metric. Now, as you know, I came from Indonesia, so I learned my physics more in metric. Okay, I don't really use the feet and then what's that? Feet and then pound. I'm sorry, I don't do those kind of things. Okay, now that's for the hydrostatic pressure at the bottom. Now here's the issue which we will see a lot in our class today. What happens if we want to find the hydrostatic pressure hydrostatic force at the smaller wall? the smaller vertical wall. So I'm talking about this wall here, the smaller one. Now the question becomes harder because different points on this wall has different pressure. Different point on this wall has different pressure. Only those points at the same depth have the same pressure. Okay, but different points at different depth have different pressure. Okay, so the way we will compute it will be as the following. We will do the following. I need you to imagine it. I need you to imagine this. Let me redraw it here. No, that's not what it looks like. It's more like this. Okay, this is 8 here. This is 6. Now, my plan is this. I will create a strip or a line, maybe. You know what? I use this one. I create a strip here. Okay, and I will compute the force experience at that strip. Okay, so you imagine that later on I will add all these strips together. Oops, no, I don't want this one. I want this color. Well, basically, I will get a lot of strips that I will add later on. Now, what is the pressure experienced at this strip? The pressure experienced at this strip is the depth. Let me call that X. Okay, the pressure experienced at that strip is X times rho times G. That's the depth. Okay, multiply by the width. Multiply by the width. So the force at that strip, only at that strip, is equal to X rho G times the width 8 times dx, if the thickness here is dx. If the thickness here is dx. So the total force will be the integral from 0 to 6 of X rho G times the width dx. Like what I told you earlier, I usually just leave my answer in rho G. So basically what you need to integrate is dx, which is the depth, multiplied by 8, which is the width at that depth. Okay, it turns out that in this case, the width at any depth is equals to 8. So that's 36 times 4 rho G. That's 144 rho G. Pay attention here. The rho G is the one to convert that into multiplied by the density and the gravity. This X here is the depth. The x, the depth is moving from x equals to 0 to x equals to 8. I'm sorry, x equals to 6. And this 8 here is the width. That's the width at depth x, which happens to be constant. How do we use this when the shape of the wall is not a rectangle? Let's say, for example, I pick question from the book. Let's say, for example, we do number 4. Number 4, we have the body in the water. Let's say this is the water. And then I have a right triangle submerged into the water vertically. Let me just do it this way. This is 4 feet. This is 3 feet, and it is submerged 1 foot below the water, the surface of the water. 1 foot below the surface of the water. Okay, and we want to compute find the hydrostatic force. Now, there are many ways to do this problem, and it gives us the same answer. I will show you 3 different ways to do this problem. So is this problem only 2D? You will see that's basically the case, but you need to imagine as if we have the following situation. Imagine if I have a pool. Imagine if I have a pool, okay, and then on one of the wall we have that triangle. Okay, now suppose this pool is full of water. Okay, and then that triangle is actually the door for the sink. It's like some kind of like triangular door. Okay, and the depth is 1 foot. The height here is 3, and the width here is 4. So basically, imagine if this triangle here is basically the shape of this triangle. Now the question then is, how much force this door or this hole, the triangle hole, supposed to, how strong can it sustain? How much force it needs to be able to sustain? Are you following me? So it is true that the shape is 2-dimensional, but it has to be understood that the triangle is submerged vertically into the water. Okay, yeah, so how much force? So if you actually put this put somebody there, right? Okay, then how much force that person need to push against that wall to hold the water? By the way, this then gives us the foundation to how much force the wall of a dam should be able to sustain. You know, dam, not not du, but then for the reservoir. You see what I mean? Okay, because if you think about it, that the dam, then you should have the wall, right? And then the water here. The thing is, if this is too deep, you try to contain too much water, right? Then your wall have to be very, very strong. You know, your wall have to be very, very strong. What you don't want is, you don't want to create a wall like this for your dam. No, no way. Why? Because if your wall looks like that, it will crack here at the bottom. It will crack there. Okay, you want to create a wall where the deeper it is, the stronger it can sustain the pressure at the bottom, right? That's why then the wall will be at least something looks like this. Most of the time, they actually make it like this. You see what I mean? Does it make sense now? Why? Because the deeper the deeper the water, then the more force, the more pressure at the bottom here, okay, and it creates more force pushing into that direction, right? Does it make sense now? Okay. Now, so what we are learning here has something to. This is not all though, because if you think about it, then the reservoir, it's not hydrostatic; it's actually hydrodynamic, in the sense that the water is actually moving. The nice thing is when the water is moving, the pressure is actually less. The pressure is actually more if the force, if the water is actually not moving. Okay, so imagine that situation. Now I will enlarge that figure to help us computing the force. So let's say this is the water, this is the triangle. Okay. One of the art of doing this kind of problem depends on how you choose your point of reference. Okay, your how to say that, the water, where, not the water, where, what is your variable, where your variable starts. For example, your water's actually, the surface of your water is here, right? Let me use blue. The surface of your fluid is actually here. Agree? Okay, let me just get rid of this. The surface of your fluid is here. And this is one food. This is one food. So if you call this your reference x equals to 0, right? Then your domain of integration later on will start from 1 up to 4, right? This, because this is 3 feet, right? Your domain of integration will start from 1, the depth will start from 1 up to 4. Does it make sense? And for every depth x, let's say this is my x, I need to find out what is the width at that time, at that point. Okay, I need to find the width at that depth. Now, then suppose this is x, then what is this? That's x minus 1. Is that right? How about this? That's 4 minus x. Because the whole thing is 4 minus the depth x. So this is 4 minus x. Right? Now then we use a similar triangle this is 4, this is 3. If this is 4 minus x, what will this be? Let's call it W. Okay, so 3 over 4 equals to 4 minus x over W. Are you with me? Similar triangle. I use similar triangle. And then I solve for W here. So W is equal to 4 over 3 times 4 minus x. Then my hydrostatic force will be rho g integral from 1 to 4, the depth x times the width at that x, which is 4 over 3, 4 minus x dx. Okay, now I don't want to compute that into numbers. I don't want to compute that into numbers. I will just leave it in rho g, okay? And I have my reason. This will be 4 over 3 rho g, and then I integrate that, I will get 4x minus 1/2 x squared from 1 to 4. That will be 4 over 3 rho g, that's 16 minus 8, 4 minus 1/2. That is 4 over 3 rho g, 8 minus 4 is 4 plus 1/2, 4.5, so 9 over 3. So that will be 18 over 3 rho g. Confirm my computation. And I will just leave it like that. Okay, I will just leave it like that. You got same answer? Okay, good. Now that's the first approach where you use the surface of the water as the point of reference x equals 0. That's the first take. The second take. The second way to do it. The second way to do it. Let's say this is my water. Okay, and then this is my triangle. This is 3. This is 4. Now I will choose my reference x equals to 0 here. Okay, now this is 1 foot, right? So if my x is this big here, if this is my x, if that's my x, then what will this be? Three minus x. Okay, now using that information, I set up the similar triangle. 3 over 4 equals to 3 minus x over the width. So the width is equals to 4 over 3 times 3 minus x. Okay, now then what will my force be? My force will be in rho g integral. I start from x equals to 0, start from x equals to 0 to x equals to 3. Is it right? X equals 0 to x equals to 3. But when this is my x here, what is my depth? How deep it is? The depth will be x plus 1. Okay, the width will be 4 over 3 minus x dx. This is the depth. This is the width at that depth. Now, if you integrate it this way, you will get the same result. Hold on, am I recording this? Okay. Now, let me integrate this. This is 4 over 3 rho g. Okay. Now, instead of integrating it, let me do substitution. What do you think? Once I do substitution, then you will see we get the same integral, okay, and therefore the result should be the same. Let me do u equals to x plus 1. So du equals to dx, right? So this will be 1, this will be 4, this will be u, this will be 4 minus u du. But that's basically the integral we see up here. You see that? That's the integral we see there. The same integral. So we should get the same result. Does it make sense? Okay. Let me just say dot, 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 same answer. So I have two approaches already, basically using two different reference x equals to 0. The first one here, the x equals to 0, start from the surface of the water. My x equals to 0 here start from the top of the triangle. The third take. I hope I confuse you enough. So which way is the best one, Thomas? I don't know. Experience will tell you what is the best. Okay, I just show you that simply because I do it differently doesn't mean I get it wrong. No. Okay, that's why I want you to realize that using solution manual will disable you from being creative. Using solution manual will disable you from being creative. And honestly, I say that with a big concern. Why? Because compare your age and my age, you are at the age where you're supposed to be more creative. So teaching you only to do it with one method will kill your creativity. It's not good for you. Okay. Now I know when you see how I grade your tests, I'm kind of like quite strict with your notation. Okay, but you don't realize how many different ways of doing the same problem, and having 16 people writing the test. Okay, some of them leaving a lot of blank, but for those who actually did the test, like really know how to do the test, like if you have two different people really know how to do the test, you will have like at times you have two different ways, three different ways to do something. Okay, now the third take, I will choose my x equals to 0 here. Okay, so x will move up from there. This is 3 as we know earlier. This is 4. So the width, the equation for the width will be 3 over 4 equals to x over width. Let me change the x instead of there. Let me change the x here. Now you can see it better. Right? So the width is equals to 4 over 3x. Right? Now, if this is my x, what is my depth? How deep it is? The total is 4 here, right? 3 plus 1. Okay, so the depth here will be 4 minus x, right? Then we start the integral. The force is equal to rho g integral. My x will be moving from x equals to 0 to x equals to 3. My depth will be 4 minus x. My width at that depth will be 4 over 3 times x dx. Okay, of course you can compute it from here to show that we get the same answer. But instead of doing the computation, I kind of like try to cheat you. How about we do some, actually no. How about if we do some, some substitution. Let's do u equals to 4 minus x. So du equals to negative dx, right? Now my integral becomes from 4 to 1. This is u, 4 over 3, 4 over 3, 4 minus u, negative du. Now I will reverse the order of integration, the limits of integration. Rho g integral from 1 to 4, u times 4 over 3, 4 minus u du, which is exactly what it looks like here, except I use u. Okay. Now the thing is, I don't think the first method will be the best one because I don't like the, I mean, put it this way, I prefer if I have a limit x equals to 0. If one of the limit is 0, it will be a lot easier to compute, right? I mean, this is easier to compute. I mean, you can try. It's easier to compute rho g 4 over 3 integral from 0 to 3, right? Okay, so I will get 4x minus x squared. Why do I prefer to have 0 as one of the limit of integration? Well, because if it is polynomial, you put in 0, it's 0. Okay, so I will get 2x squared minus 1/3 x cubed from 0 to 3. That's 4 over 3 rho g. This is 18 minus 9. Huh? Is it right? Yeah, 18 minus 9. So that's 12 rho g. Hey, why I get different answer? Am I missing something? Hold on, this is 6 rho g. I'm missing something here. I'm missing something here. I'm supposed to get the same one though. Or am I making mistake here? Oh, I make mistake here. This is a good thing I checked it. No, this is totally wrong. I forgot to integrate this. This is still under integration. Duh. Right? That's still under integration. This is x squared here. Am I right? So this is not correct. Oh, shoot. Good thing I checked. So this is 2x squared minus 1/3 x cubed from 1 to 4. You say you get the same answer, and we get the same wrong answer. Okay, so this will be 8, I'm sorry, not 8, 16, 32. That's 32 minus, what's that? 64 over 3 minus 2 minus 1/3. That's 32. So that's 34 over 3 rho g. That's 30 minus or plus 21. 63 divided by 3. So that's 9. Yeah, that's 12 rho g. Which is the same to what we get here. How about I have only 4 minutes left, so I guess on Wednesday I will do more problems, but let me do one more right now. Number 8. So this is the surface of the water, and then I have a trapezoid sink into the water vertically. This is 4, this is 1 here, and this is 1 here. This is 2 here. We'll compute the hydrostatic force. So if we think about it, the one really matter is the one under the water, right? The one under the water. This is 1. This is 2. Okay. Now, why do we need that 4 and 1 up here? That is to help us to find the ratio. Suppose instead, you may be tempted to say that you want to have your x equals to 0 here. Fine, that's totally fine. When your x equals to 0, what is the width? When your x equals to 1, the width is 2. Actually, maybe I prefer to do it this way if I extend it further. When x equals to, I'm sorry, this is x equals to 1. When x equals to -1, the width is 4. And it is a trapezoid, so the width is actually decreasing linearly as you go deeper, right? So can you tell what is by looking at that, can you tell what is this here? What is the width when x equals to 0? I think that's 3. Okay, so notice that when x equals to 0, the width is 3. When x equals to 1, the width is 2. Can you see the relationship? And it has to be linear. Why 3? Because when you extend one more further up here, and this is 1, the length here is 4. Right? Okay. I don't need that 3 actually. There are more than one way to do this, the width. But I think the one I'm showing you here is the easiest approach. It has to be linear, therefore the width must be 3 minus x. Right? When x equals to 0, the width is 3. Actually, when x equals to -1, so if you go backward there, -1, the width is 4. Right? Okay, it's 9:50. So let me just hit it hard right away. So my force will be, my hydrostatic force will be integral when x equals to 0 to 1, rho g, let me put it inside for now. When my depth is x, my width will be 3 minus x. Yes. That's the setup. Okay, and then from there you compute yourself. Okay, suggested homework from 8.3a. I would like you to do number 3 to number 11. Practice, practice, practice. And 8.3b, I would like you to do number 25 to number 35. Do the odd ones. Then on Wednesday, we will come back here, do more problems from here. And there are nice things to know on this hydrostatic pressure. Okay. It's actually quite fun for me. It's fun because not with the student, it's just like, it's fun because if you start with the correct reference, x equals to 0, then you can integrate it a lot faster. Yeah, you can integrate it a lot faster. Okay, that's for today. See you then on Wednesday.